We can also use Curry to plan stereo EEG contacts. We can navigate through the image data and define a target location. Create a location by using the keyboard shortcut Control-I, and also define an entry point. And then here in the intracranial electrodes dialog, define how our stereo EEG electrode looks like, number of contacts and spacing and some other parameters, and then click Create. We can do this with multiple electrodes. We can create another one. We can also use this display to specify the entry point. Create another electrode, and so forth. I'm just creating a few just for demonstration purposes. And now one of the interesting or nice features of Curry is that we can display oblique cut planes. We can right click and switch an oblique view to automatic, for example. And now whenever I click any of my stereo EEG contacts that I have planned, this slice here will show the needle in its entirety, because the cut planes through our image data cube are no longer orthogonal, but they follow the trajectory of the stereo EEG contact. So it's very nice or very easy to follow the structures that a certain stereo EEG contact goes through. We can also display a safety margin to make sure we are not hitting any vessels or damaging any other tissue. And once we are happy with the planned stereo EEG contacts, we can save them in any of the coordinate systems that Curry supports, and one of them is also for the ROSA system. Or we can export the MRI data with the SEEG contacts embedded and push this image to our PAX server to, for example, be imported to a navigation system. And next I want to show an example of a stereo EEG study where we have our stereo EEG recording here, and we can add image data to our study. Again, in this case, this comes from a folder. Let's add the MRI first. And again, this is the first time we are importing this image data set, so we get to mark the landmarks. I'm just doing this real quick. Once we have the MRI data, we can also insert CT data. And for the CT data, which contains the stereo EEG contacts, we can use the auto-detect method to automatically have the MRI image and the CT image co-registered together. And this is a preview of the co-registration result, where you see the MRI image in green overlaid over the CT image in gray. And yeah, the bone structure you can see follows very nicely. So it looks like the co-registration worked very well. And now we have both image data sets in our study, and any location I mark in my MRI data will be the exact same location that is marked in the CT data. So we can make use of the information from our CT data to generate the locations of our stereo EEG contacts. And there are multiple ways to do this. One is we can use the maximum intensity projection view to again select the target point of one of our needle and then another location along the trajectory, and then create a depth electrode that matches the properties of our electrode. And we can do this for all of the electrodes that we have in our file, but we have to make sure to do this in the order that they were actually connected to our amplifier during the recording. So we can do this using the maximum intensity projection image here, or we can also create an intracranial voxel mesh. And now we can use this display as well to mark the contact, the target point, and another point along the trajectory of our stereo EEG electrode, and then create the needle. And once we have done this for all of our stereo EEG contacts in our file, we can apply the locations to our stereo EEG recording, and we are then able to see the amplitude of each and every stereo EEG contact in a color-coded way. And here in this recording we have a few bad contacts here, which we can easily disable by just clicking on their labels. And now we can review the stereo EEG data in an anatomical context. And we can again make use of the oblique view functionality, where we can now click on any of these stereo EEG contacts here, and this slice that we enabled the oblique view for will show us the contacts in an oblique cut. So we can now navigate through our recording and see which electrodes show the highest or lowest amplitudes. We can also very easily create montages that either show all needles separated, ordered and separated. So we can have a butterfly plot where each and every line represents the waveforms of one needle. Or we can also generate a montage that shows bipolar derivations, which means that now we see difference waveforms between neighboring contacts, and review the data using this display. Another option we have is to display a filter envelope, for example for ripple or fast ripple activity. We can compute an envelope that then can help us to find contacts that show the strongest signal in the frequency range that we have selected here in our filter dialog. And as a last note, it is also possible to use the stereo EEG data to perform source localization, and for this we would have to create a finite element method model, which can also be done automatically in Curry.